It is entitled Powder Method for Detection of Latent Fingerprints. In this module, we are going to learn about the powder method for detection of latent fingerprints. This is important because this is one of the most simple methods of detecting fingerprints at the scene of crime. After studying this module, you will be able to know that the significance of the most widely used powder technique of fingerprint detection and its importance. The mechanism of fingerprints detection by powder compositions. The broad classification of powders used in detection of fingerprints. We now come to the introduction. The powder method for identifying latent fingerprints includes the application of a finely divided formulation to the finger mark impression, usually by a camel hair brush. The powder gets involuntarily stick to the sweat residue, signifying the ridge pattern. The furrows, which do not have fingerprint residue, will not stick the powder on itself. The final result is that the powder combination sticks to the ridges but is effortlessly blown off the grooves. As the powder is usually colored, the ridge pattern turns out to be noticeable and the latent fingerprint is known to be developed.
Historical. The use of fingerprint powders times back to the last era of 19th century. Sir Edward Richard Henry, who devised the fingerprint grouping formula, suggested the use of mercury, composed, and graphite-based powders. The previous formulation, known as hydrargyrum cum trita, was consisting of 1 part of mercury and 2 parts of chalk by weight. The powder was suitable for non-absorbent surface like glass and dark painted or lacquered utilities for mounting latent prints. However, the formulation was withdrawn in 1967 since the mercury contained may be a health hazard. Moreover, it was ineffective for evolving prints on gold ornaments, as mercury reacted with gold and stained its surface. The graphite composed powder was really useful for mounting imprints on silver painted objects, but this powder was inhibited as it was untidy to use, chiefly if the examination was to be carried out in open and a high wind was blowing. Next is mechanism of technique, the application of finely distributed material and the subsequent elimination of the extra powder by brushing, blowing, or tapping has been the universal technique of increasing fingerprints on non-absorbent surfaces as the early times of fingerprint technology. The technology lies on the power-driven adherence of fingerprint powder to the moisture and oily substances of the skin ridge deposit. The adhesion of powder formulation to fingerprint residue is governed by the pressure deficit mechanism. If a powder particle is soaked only on its lower side by the sweat deposition, then owed to the arc of meniscus, there will be a pressure deficit inside the droplet, causing the particulate to adhere. The major role in adhesion is of electrostatic attraction between the sweat residue and the powder particles, resultant due to frictional charges, albeit a minor one. The efficiency depends upon size and shape of the particles with which the powder adheres to the ridges that compose the formulation. Small, fine particles adhere more easily than large quartz ones. Consequently, most formulations are composed either tiny rounded particles about 1 micrometer in diameter or of fine flake particles about 10 micrometers in diameter. Of late, nanoparticle size powder compositions have proved to be very effective in lifting fingerprints. A sample fingerprint developed with the aid of a nanoparticle based composition incorporating crystal violet stain is depicted. As the age of the fingerprint residue increases the moisture, thus it leaves the deposition more viscous components which incline to evaporate. The similar phenomenon is seen in warm climates. Hence, aged prints in tropical climates are comparatively problematic to progress by powder technique. The drying rate, thou, is not dependent on the relative humidity, representing that the sweat residue has low water content adjacent the surface. Next is color selection. Black is by far the most commonly used latent print powder color. Black powder is manufactured from a variety of carbon based powders with a binder added for stability. This carbon based powder readily adheres to the oily residues generated by contact from fingers and other body parts. Black powders are easy to apply to many surface types, porous and non porous alike. Because of its versatility, black powder is the workhorse of latent print processing. Before these powders advanced through further scientific development, there were few other colors available. Black and aluminum were both powders of choice, but black was by far the most popular. Regardless of the surface type or color, black powder was spread and prints were developed. Examiners would then use a very bright light source to visualize the prints, especially on darker colors that lacked contrast. The developed prints were of exceptional quality. The only problem was that they simply could not be readily seen. The convention today is to use a powder color that provides a visual contrast to the surface being processed. Dark surface is equals to light powder and light surface is equals to dark powder. Rather than using black powder for everything, other colors such as white, silver, gray, aluminum, or bichromatic can be used to process almost any surface that may be encountered. White powder works especially well on glass, chromed metals, plastic bags, and dark colored surfaces. Aluminum powder performs best on glass, plastic, and rubber. Bichromatic powder, on the other hand, is typically a combination of black and aluminum powder, although some manufacturers combine the black with a variety of other colors. The idea behind the creation of the bichromatic powder was to assist the examiner with multicolored surfaces. When processing with bichromatic powder, developed latent prints will be seen as black ridges on the light parts of the surface and light ridges on the dark parts of the surface. Once these prints are lifted, they will always visualize as dark ridges on a white backing card. Next is material selection. In addition to the color of the powder, the physical composition of the powder also varies depending on the examiner's needs. Powders can be characterized as conventional, that is, colorant and base, magnetic, that is, colorant and iron shavings, and fluorescent, light stimulated, colorant and base. Conventional powders are the most common type of powders used in crime scenes and are typically applied with a fiber or hairbrush. They are generally inexpensive, cover a large area when applied with a brush, and readily develop prints on most non porous surfaces. The main concern with conventional powders is that they can create a mess. Black powders are generally very light and airy, so the particulate can become airborne at the slightest flick of the brush. Conventional powders are not designed to work on porous surfaces like paper, but are used in the field nonetheless. Fingerprint residues left behind on paper are best treated with a specialized chemical process. The time it takes to process a print on a porous surface from the time of the print deposition allows some of the moisture to evaporate. So, dry powder processing may not produce optimal results. Magnetic powders are designed to work on both porous surfaces and non porous surfaces, including plastics, styrofoam, and rubber. Technicians using magnetic powders develop latent prints without the need of a brush. A magnet embedded inside a plastic or non-porous metal wand attracts the magnetic fillings and creates a clump or ball of powder. Wrapped around each of the iron fillings is the colorant. The iron fillings then rub over the surface, depositing the colorant where it comes into contact with the oily residues. This process develops the image with little or no abrasive contact with the residues, unlike using fiber or hair brushes. Magnetic wands can be used in many situations. However, upside down processing does pose a unique problem. The magnet does a fine job of managing the powder when the wand is held in a normal magnet down position, but loses its effectiveness when used upside down. Magnetic powder is easy to clean as a surface is processed. Small bits of the iron fillings will dislodge from the band and remain on a horizontal surface. To clean up these bits, simply pass the wand over the fillings to collect for reuse or deposit them back into the jar. It is important to remember that as the fillings are returned to the jar and reused over time, the associated colorant will eventually diminish, leaving only iron fillings in the jar. Fluorescent powders were developed to use with a variety of alternate light sources ranging from small 1-watt ultraviolet lights to multi-watt lasers. These powders work especially well on raw surfaces where normal conventional powders may paint or clog these surfaces and render prints that are not distinguishable from the surface. Household woodwork, convenience store counter surfaces, and multi-colored non-porous items respond particularly well to processing with fluorescent powders. The colorants found in fluorescent powders are treated dyes that react to ultraviolet or UV, and purple or blue bands in the visible light spectrum, typical for crime scene work. The hues of the powders can be matched to the color of the surfaces being processed and the wavelength of the light source being used. This coupling helps flatten or eliminate any background interference that may occur from surface coloration or contaminants. Fluorescent powders are best applied with a feather dust. The minute barbules or soft parts of the feather are perfect for holding just the right amount of fluorescent powder to develop the print without over-processing the background. When using fluorescent powders, less is better, as over-processing cannot be easily corrected. It is not recommended that fiberglass or hairbrushes can be used, as they will deliver too much powder to the surface, and the visual overload may result in the loss of any detail or detection. Fluorescent powders are also not recommended for large area processing, if only for the over-processing reasons stated earlier. A few years ago, spray powder hit the market. Spray powders deliver a very localized and controlled application of powder. The idea behind this product evolution was to give the technician a specialized tool to allow for spot processing on certain surfaces. It was not intended to replace conventional powders and brushes already available. The measured portion of powder delivered by a short blast from the can provides enough powder to allow the prints to develop without over-processing the background or the prints themselves. The spray powder is contained utilizing a containment tent to keep the powder in a constricted space so it will not broadcast over the area being processed. This allows for relatively clean processing of crime scenes that minimize both property damage and possible respiratory irritation from exposure to powder. Next are the application procedures. Before the use of powder formulation, the surface must be investigated visually for the fingerprint impression. This is usually done with the aid of an intense light source in concert with a magnifying glass. The print should first be photographed using an appropriate filter. Next, the relevant powder should be applied within a circular motion by a fingerprint brush. Attention should be given to prevent the distorting of the imprint. The excess powder must then be removed by dusting the surface with a mild tapping. The settled print should once again be photographed. Finally, it should be lifted with a tape and preserved for record. Application of powder to fingerprint by brushing is a well established technique but has one disadvantage. Contact of the brush with the fingerprint has an unavoidable damaging effect, so that a degree of attentiveness is mandatory by the fingerprint expert. It has been assessed that around 10% of latent fingerprints formed at crime scenes through convention powder dusting procedures are difficult to identify. Powder may be applied without using a brush. An electrostatic depositor, atomizer, or aerosol spray may be used instead. For electrostatic deposition, the powder is poured on the surface of an electrode held about 2.5 centimeters above the surface, imposed with the finger mark. A potential gradient of about 12 kilovolts is preserved between the electrode and the surface. The powder on the electrode becomes charged to the polarity of the electrode and is enhanced towards the surface, where it is discharged and obtains the polarity of the surface. The excess powder is attracted back to the electrode and is discharged there. Magna brushes and magna powders may also be used to avoid the problem of bloating. Magna powders are made by integrating quartz spherical iron particles in the conventional powders. The magnetic irons perform as a carrier for the non-magnetic formulation, forming a brush when the powder is picked up with a magnetized applicator. On brushing the imprint impression, only the fine particles of the formulation stick to the fingerprint residue. Once the print has been made, the excess powder can be removed from the applicator by removing the magnetized steel rod. The magna powder may be switched by magnetic flake particles to enhance the performance of magnetic applicators. In such combination, the quartz iron particles are switched by magnetic flakes that are attracted to magnetic applicator. Each and every magnetic flakes picked up by the applicator are available for fingerprint formation, like standard magna powders that contain only around 1% of fine particles that can stick to the fingerprint remains. The magnetic flakes are precisely useful for print development on rough or porous surface, like as painted walls, polythene, and paper. Next, we will study about regular powders. These powders comprise of a viscous polymer for linkage and a colorant for contrast. The adhesive gets stuck to the moistness and oily constituents of the sweat residue by the pressure deficit mechanism, while the colorant gets adsorbed on the adhesive. In this manner, the rich pattern is pictured. The commonly used adhesives are starch, kaolin, rosin, and silica gel. The colorant may be an inorganic salt or an organic derivative. Formulation containing ferric oxide and rosin, manganese dioxide and rosin, titanium and kaolin, lampblack and fuller's earth are some of the common examples of inorganic based fingerprint powders. The functioning presentation of the arrangement may be enhanced by coating the powder onto fine quartz or plastic particulates. A black powder comprising iron oxide, quartz, kaolin, and carbon soot is an example of coated dusting formulation. Over the years, it became manifest that commercial fingerprint powders containing inorganic salts of mercury, cadmium, titanium, lead, manganese, etc., pose an occupational hazard to the user. As a result, the organic based formulations become more popular. These formulations generally contain an organic dye as the colorant. For improved results, fluorescent and laser active dyes are used. Formulation containing fluorescein, eosine Y, and rhodamine B are some of the common examples of organic grounded fingerprint powders. Metallic powders. Powder formulations have been in use for a significant time, comprising meshed metals. Their benefit is that they have good shelf lives as compared to the organic based powders. Their weaknesses is that the metallic components elicit toxic effects to the handlers. Silver powder containing aluminum flake and quartz powder, gold powder containing bronze flake and powdered quartz, and gray powder containing meshed aluminum and kaolin are some of the examples of metallic dusting compositions. Additionally, pine lead powder has been used for latent detection with X-ray electronography and autoelectronography. A noticeable number of powder formulations comprise natural or synthetic organic products that fluoresce or phosphorus upon exposure to ultraviolet light or laser light. The advantage of such compositions is that they are useful for visualization of latent prints deposited on multicolored surfaces that would present a contrast problem if evolving from conventional powders. Furthermore, these can be used for mounting weak prints. Their drawback is that these can be infrequently used in fieldwork. Some observed organic compounds which are mostly used for the powders are acridin yellow, acridin orange, coumarin 6, crystal violet, Nile blue, rhodamine B, and rhodamine 6G. Lanthanide complexes comprising the luminescent powders on the position of organic derivatives has now been formulated. Lanthanide complexes propose numerous benefits, plus benefits from great Stokes shifts, long luminescence lifetimes, contracted emissions, capability of successive assembly of complexes, and chemical variability of ligands. Moreover, such powders are appropriate for discovery of latent fingerprints on hard surface such as wood, masking tape, and polythene.
Finally, we come to the summary. Powder dusting is the easiest currently available procedure for detecting latent fingerprints. It is used by fingerprint experts as one of the oldest methods. An unprofessional hand can develop the fingerprints by brushing and tapping. It does not need any sophisticated equipment. The recognition of prints can be done by both at the scene of crime or in the laboratory. Beyond all, powder formulations are pliable to alteration to suit the conditions. Thus, it is possible to prepare powders which are economical, non-toxic or luminous in a wide group of particular size, color and composition. We will further learn that there is another method called iodine method of fingerprint detection. Iodine method is a vapor phase method. The vapors of iodine, which is a sublimable solid, they settle down on the latent fingerprint and develop brown color finger marks. The advantage of this method is that it is very easy to use, more easy than even the powder method. The disadvantage is that fingerprints fade out within next 10 to 15 minutes. Yet, iodine is still the preferred method because if fingerprints fail to develop by this method, the powder methods can still be used. On the other hand, if powder method fails to develop fingerprints, iodine method becomes futile. Moreover, recent research has shown that iodine fingerprints can also be rendered permanent. This is based on the premise that all the organic compounds of iodine are brown in color. We are not talking about inorganic compounds. Potassium iodide, of course, is colorless. Yet all the organic compounds starting from iodobenzene and ending at iodonaphthalene, they are all colored. If we search for any organic compound which like iodine is sublimable and the two chemical entities are made to react in vapor phase, the chances are that the product so formed will not be sublimable, and since it is colored, it will settle down on the ridges and impart brown color to it. When we talk of sublimable organic compounds, I suppose the first two examples which come to mind are naphthalene and camphor. Naphthalene and camphor both react with iodine, but it's better to rule out iodine because it is quite toxic in nature. We have proposed that when iodine and camphor they react with each other, they produce 2-iodo-camphor. This compound is brown in color, the color is quite sharp, the color is quite bright, and it is non-sublimable. We have conducted experiments in our laboratory and we have shown that 2-iodo-camphor remains stable on the finger ridges for an indefinite period of time. That is to say that the iodine developed fingerprints do not fade out with time and can be made permanent.